So are you aware of there is something called universality of uniform distribution? No? Okay. Okay, so let me first explain what is universality of uniform. So what, it's actually a wonderful concept. So suppose you want to generate random number from some distribution, okay, and let's say it's some triangular distribution. How will you generate random number from a triangular distribution? So actually this particular proposition, universality of uniform, gives you that power. It tells you that if you know how to generate random numbers from uniform distribution, you can actually generate random numbers from any distribution of your choice. Okay, of course, if you want to use if you want to generate random numbers from binomial, geometric, hypergeometric, negative binomial, or any other commonly used distribution, then of course you can use R directly. Okay, there is no problem. But let's say if there is some distribution for which R does not have a direct command, you know the density function, but you don't know how to generate random numbers from that distribution. So how will you use the power that you have of random number generation from uniform distribution to generate random numbers from distribution of your choice? Okay, that is what is interesting about universality of uniform. Yeah, absolutely, using the CDF, absolutely. Okay, so let's just see how we do it. Okay, let me first tell you the result, and then we'll just use that to generate random numbers from, let's say, some distribution. I'll just specify the distribution also, and we'll see how to generate random numbers from that. Okay, fine. Okay, so let me erase this. Okay, so first let me state the result. Okay, so the result is the following. And in the end, I want to generate random number from, let's say, this distribution. Okay, suppose I want to generate random numbers from a distribution whose density function looks like this. This is what I want to do in the end. Zero to 2. Okay, it's from 0 to 2. And what should be the height here for this to be a valid density? Half, right? Because is it half? Just a minute. Yeah, 0 to 2. Okay, so just a minute. So it's actually 1. Sorry about that. Because it's a triangle, right? So yeah, half base into height. So height is 1. Base is 2. So half base into height, that's 1. So basically you want the area under the density function to be 1. So in the end, I want to, let's say, generate random number from this. Of course, the idea that I'm telling you here works for anything, but just for simplicity, we are just using this. And I'll tell you the general way in which you can actually just apply that particular approach to generate random number from any distribution of your choice. Is that okay? And please note that this is a PDF, not the CDF. Okay, I want to generate random numbers from distribution whose PDF is this. Is that clear to everyone? Yes or no? Okay, great. So let me now tell you the result. Okay, so this is the result. Okay, suppose X has a CDF fx. Okay, suppose X has a CDF fx. I'm assuming right now X is a continuous distribution. Okay, for discrete distribution, of course, you can also use uniform, but the thing is a little bit more involved. But for continuous distribution, you can easily do it very quickly. Okay, using the result that I'm telling you right now. Okay, suppose you want to generate random numbers from capital Fx. You want to generate random number from capital Fx, which is the CDF of random variable x. Okay, fine. This is our job. This is what I want to do. Okay. So I'm going to use the fact that Fxx, this transformation, this kind of a weird transformation. You know what you did is you use the CDF. CDF is a function. Okay. X is a random variable whose CDF is Fx. You plugged in X in its own CDF. So you got a random variable because it's a transformation of random variable X into Fxx. Yes or no? The input is a random variable, so output is also a random variable. Yes or no? Okay. So what can you say about the distribution of this random variable? It's actually a uniform 0, 1 random variable. Let's prove it. It's just a 2 lines proof. Let's prove that it's a uniform 0, 1 random variable, and then we are going to use this fact to generate random number from that triangle distribution that we have just we'll use some kind of an inverse. Absolutely. Okay. So let's just do this. Okay. So Fxx. Okay. Let's figure out the distribution of. Let's call this U. Let's figure out the distribution of this. Let's prove that it is actually uniform 0, 1. Okay. So if you want to find the distribution, first of all, Fx is the CDF, and CDF only takes values between 0 and 1. So one thing is pretty clear, that the values that it will take will be between 0 and 1. Okay. So Fu. So what is the CDF of U? Okay. Ideally, I should get the CDF of U as increasing function, right? I mean, in fact, it's linear and increasing. Okay. So I should get Fu A as A, right? For A between 0 and 1. Yes or no? Okay. So let's see if you're going to get that or not. Fu of A is probability that U is less than or equal to A by definition. Okay. Which is equal to probability that Fxx is less than or equal to A. Okay. Which is equal to the probability that X is less than or equal to Fx inverse of A. Right. The reason is because Fx is strictly increasing in this range. So clearly, and yeah, so the inverse is defined in this range. So we can actually take the inverse both sides. And what is this? This is actually the value of the CDF of X at Fx inverse A. So you're going to get Fx of Fx inverse A. And Fx of Fx inverse A is A. So, and what is the density of U? So FUA is the derivative of the CDF, which is 1. Okay. So Fxx is uniform 0, 1 because the density is 1 between 0 and 1. Yes or no? Have you understood this? This is known as universality of uniform. Okay, this is universality. So basically, you take any CDF, okay, take any random variable with some CDF Fx, put that random variable in its own CDF, you will get a transformation which will always be uniform. Okay, that's universality of uniform. Now, let's come to the task. How is this going to help us accomplish what we are interested in? Okay, now this tells you that if U is Fxx, then Fx inverse U, then Fx inverse U has the distribution Fx. Because if U is Fxx, X is Fx inverse U. Is that okay? So if X is Fx inverse U, then the distribution of Fx inverse U is Fx. Okay, so let's just use this. Okay, let's use this to generate random number from the distribution of our choice. Okay, so this is what we are interested in. We want to generate random numbers from this triangular distribution. Okay, so let's use this to generate random numbers from this. Okay, so first we have to figure out the CDF. Remember, because we want to take the inverse of the CDF of F. So we want to take the inverse of the CDF of X, right? So we have to first figure out the CDF of X. Here, this is the PDF of it. right? So how do you get the CDF from the PDF? By taking the integral. Okay, so x, so let's first figure out what is the PDF. Okay, what is the value of the PDF here? Fx x equals half x, right? For x between 0 and 2. Yes or no? Okay, this is the distribution that we are interested in. Okay, let's figure out the CDF. Okay, so what is the CDF? Fx x is equal to integral from 0 to x of half t dt. Okay, so I'm just changing the variable names because if this is x, I cannot keep x over here also. So this is going to be t square by 4, which is x squared by 4, right? X squared by, just check this.
Yes.
This is x squared by 4. Okay. Now, what is the inverse function of x squared by 4? So if y is x squared by 4, what is x? 2 root x is 2 root y, right? Yes or no? That's it. Use this. We'll use this. Okay. Okay. Let's now do this, and let's generate random numbers from this, and then we'll plot, you know, the histograms from those plots, and we'll find the triangular type shape. Okay. Let's. I mean, you should get that right because of law of large numbers. You know, if you're going to generate a lot of data from this distribution, it will also follow the similar shape as the original population density function, right? I mean, that's what we are going to do now. Okay, is that fine? Okay, so let's keep this here. So generate random numbers from the distribution given by the density function small f x is equal to x by 2 okay, where x is in 0 to 2, right? Okay, is that fine? So I want to do this particular exercise. Okay, suppose I generate again, let's say 10,000 numbers. Okay, so n is 10,000. Now I don't know how to generate random numbers from this directly, but I do know how to generate random numbers from uniform distribution. So let me call them u. Okay, so u is r unif n. Okay, so this will give you 10,000 observations from uniform 0-1 distribution. Okay, now I'm going to take this transformation of these u, 2 square root of u. Okay, so let's take 2 square root of u, and let me call them x. Okay, 2 star square root of u. Okay, and this should work. This will give you 10,000 observations from the triangular distribution that you are interested in. Okay, so let's quickly check this. I mean, this should work. Let's quickly check this. How do we check this? Use the ggplot. Okay, so let's create a data frame of these x's. Okay, and let's run this. Are you ready? Okay. We should get what? Triangular shape. Yes. Is that fine? And between 0 and 2, you can see this. Okay, everything is exactly as per what we were interested in. Have you all understood this?
Yes.
Okay, and you can see that the height is 1, and yeah, because it's a random number thing, so of course it's never going to be precise, but it's reasonably good. Okay, you can see if you just keep running this, the main thing will be the same. Of course there'll be some sampling differences, okay, but more or less the shape will be the same, and this is because of law of large numbers. You can see law of large numbers plays such an important role everywhere. Yeah. Yeah, so if you actually just take a very large sample, then your precision will improve. Okay, so now I've taken the sample of size, you know, yeah, so it's actually 10 lakhs. Okay. Okay, so
It's lesser than 1 item to the pattern, so it's going down.
well, at 2, I think it's just because of the interval, because there's nothing to the right of the 2, so it's actually do some kind of, like left interval, right interval thing, I mean, some kind of adjustment like that, because nothing is there to the right of the 2. That's why it's just it's somewhere in the half, I mean, but you don't have to bother about that. I mean, it's just basically you're getting a triangular shape like this. Is that okay? Fine. Have you understood this? Okay, great. Okay, so this is actually very powerful. Now I mean, this is one example. Of course, you can any example now, find the inverse and do it. Generate random number from any distribution that you want. Okay, is this fine? Okay.